Uh, okay, yeah, so let me just give you my email. Um, First of all, in terms of topics, like, there's not really anything too different from what you would cover in this class versus like what you would cover like on a regular uh, multivariable section. I think mostly what I'll do is kind of like give more physical applications, things of that sort, like slightly more conceptual, but like 90% of the what you'll see here like just overlaps with what you would have seen if you had taken like the regular version. So there's not really much of a difference. So this is just my email. Is you don't have it, you can call me also Mariano if you prefer. Or professor or whatever, but I mean, I'm not really against people using my first name. So, if possible, try to avoid sending me a Canvas notification just because that gets duplicated every time you email me through the notifications, but I still reply to them if you use that. And then, yeah, I guess the plan for today was just go briefly over the syllabus, and then I'll give you kind of like a quick idea of what the course is about, and like we'll start like talking about vectors, which is the first topic in multivariable calculus. Some of you, or the majority of you, may have seen a little bit about vectors before. Um, but yeah, it's something that will be very convenient. So let me just share first, like here the computer, the screen on the computer, just to go over the syllabus. Oh, cool. Yeah, this one is mine. Okay. Oh, by the way, before we go over the syllabus, in case you didn't get a chance to read the announcement, so I didn't think it made a lot of sense to have recitation this week, so you don't have to go to recitation tomorrow. Maybe there are like first week activities of the semester that you prefer to go to. And then I'll tell you a little bit more about what's going to be happening during on a weekly basis in recitation once we start discussing the syllabus. And then usually I like to like create kind of like not an assignment quotes because it's not really graded or anything. Um, we just go hello world, where like if you want to just say something about you yourselves, like you can you can go to it, and you'll see like some people already have like mentioned where their interests are and things like that. So that gives you like kind of like a way just to get to know a little bit better the other students taking the class. I kind of did like a single um you know, and like website for like all my multivariable classes that I'm teaching this semester. So you may like some students maybe from other classes, but I'm like, probably you may run into them in different, at some other point. So it can still be nice to see what they're interested in. So, okay, so let me just start by mentioning the syllabus, like the basic things. Um, I'll probably send you like an announcement later in the week with my office hours. Definitely, at least I'll always try to show up like 30 minutes before the class starts. So sometimes that's just easier. Like if someone wants to ask me like a quick question before we begin, and also after class, you can you can ask me stuff. But yeah, I'll give you like a proper form office hours. I'll just try to find like a classroom somewhere in Livingston where I can have them. Um, Again, also for the TA, I think I'll ask Karuna to just send you like an email or an announcement with your office hours. So there's not like a official, like, we have this official textbook for the course. Like if once you get the access to MyLab, which I imagine most have used anyways from Calc 1 or Calc 2, you'll have like the electronic version. I would say that, like, not everyone will read the book. If you read the book, like, it will probably have more details than what I'll cover in class. Definitely, I will cover everything that you need to know during class. So, like, don't freak out if you read the book, and sometimes, like, there are things that I just didn't mention just because we don't have a lot of time. Like, one of the things about this course is that it really is very, like, dense. So one would like to go into a lot of details, but it's not really very practical to do so. In terms of requisites, like, really, Calc 1 is what you need to remember. There's almost nothing from Calc 2 that you need to know. Like, the course in a way is kind of like, just let's redo Calc 1, but now the functions depend on more variables. That's one way to think about it. So what did you do? What were the things that you did in Calc 1? Like, talk about derivatives and talk about integrals. So we kind of will redo all of that, but kind of in the most general context, which is when the functions depend on 2, 3, 4, 5, etc. Number of variables, which in practice, like, like 2 or 3 will be the number of variables the things depend on, just because those are like the ones that are kind of easier to visualize. But you'll see, like, a lot of the course will just kind of be following. Okay, so in Calc 1, you did optimization problems. We'll do like a version of the optimization in this course as well. In Calc 1, you did limits. We'll mention briefly limits, so that doesn't too much of a big deal in this class and things like that. So there's really very few things that you need from Calc 2. So don't worry too much about Calc 2. And in Calc 1, for, basically, like, the like rules for finding derivatives, product rule, quotient rule, all of those things are useful. Like the use of for doing integrals, but that will be useful until like the second part of the course, because we won't do integrals like for the first half or anything. So, but yeah, like you'll see, it's kind of like just redoing Calc 1 in a way. So in terms of so what I was saying is, like, yeah, the textbook, don't worry too much about that. It is, if you're reading it, like, that you see, like, it mentions a few more things than what I mentioned in class. And then this is more or less like a brief schedule or calendar for our class. So, like, our exams will be like will take place during lecture time. These are the 2 days. Once we're closer to the exam, I'll give you some practice, like all exams and things like that, then you know what's going to be on each exam. Like, typically we would have like recitation this day, but what we'll do is kind of like don't have recitation that week, and we'll just have like extra office hours, like, either Tuesday or Monday. So like a kind of more like a review. I mean, obviously we wouldn't, make conflict with conflict that will be kind of late in the day, so that the majority, most people can attend. But like the idea is kind of like just have like, I'll also give you extra office hours at the beginning of that week. So yeah, so I'll remind you later, but yeah, like the idea is just to cancel these 2 recitations, because like they don't really make a lot of sense, and just like we'll replace them with some review before the exam. Like, in general, the basic idea for like how I'm expecting the recitations to go, like, on a normal week, is that at the beginning you have like a mini quiz. Like, the quiz will be more like kind of like almost like a review. So I'll literally give you like a list of 5 or 6 problems, and the quiz will just be one of those questions. Like, it will be very, I mean, if you just go through the questions, like, there won't be any surprises. So like the quiz is just kind of like to give you like an excuse for like just reviewing some of the things we did like the week before, or the class before. And then, so like, yeah, I don't expect the quiz to take more like than say 10 minutes of like recitation, because it's just something like very fast. And then after the quiz, there will be like kind of like a workshop, just basically like all practice exams, things like that, where like it will be more like group work, but the workshop part is more like intended for you just to, like work, talk to other people. So it's more like attendance. That part of the recitation will be just more like attendance based. So if you attended the workshop, you'll get the points. Like, so you don't have to worry. I mean, it will still be graded in the sense you get feedback on what you wrote, and I'll also give you solutions. But at least that part is not going to be like numerically graded in the sense like, oh, you got like an 80. It will be like, oh, you attended the workshop or you didn't, because you don't want to get a kind of like into like these issues of how, like, how much someone in the group contributed to the solution. So it's more like to give you like incentives to just like share like whatever and don't worry too much about like who did what. So for the quiz, yeah, the quiz will be individual, but again, like it will be more like from a list of questions I give you. So there's not really like an element of surprise there. And it's just in the end, like kind of things I set them up so that if you just like look later on your own, like at how the grades work, you more or less can miss 3 recitations, I think, and still get all the points for like the recitation rubric. So it's kind of like easier to do that than just like, if you fail, you miss one of those, like that you have to ask for a makeups or something like that. So yeah, you can like miss 3 of them and you won't have any problems with the grades. And if, yeah, of course, if someone has like some sort of like bigger problem where you are not being able to attend most of the recitations, then something you have to reach out to me about, because then we have to figure out something like that. But like, I think in the overwhelming majority of the cases, 3, I think, is a good number because, like, maybe you're get sick one week or whatever, you have to be out of town, but that's all fine. You don't need to email me to let me know you cannot attend. That's kind of like what I'm trying to say. So, unless again, you kind of pass the 3 recitations threshold, and then probably you maybe want to talk to me about that. You can still obviously like talk it with the TA, but like I'm just trying to kind of set it up like that way so like it's not so stressful. You don't have to worry too much about like what happens if you miss a recitation. And besides that, like so in terms of like the how the grading criteria for these courses, like we have like these workshop quizzes which will run kind of like I just explain it to you. There's like the MyLab online homework. If someone is having issues like signing on to MyLab, you can let me know after class. The idea there, like again, probably most of you have already seen it in some capacity or the other, but like the way I set them up typically is that if you complete 80% of the problems, then I kind of like curve it and you get like full score on MyLab. By 80%, I just mean like of the totality of the problems, meaning that you could get like 100% in the first few assignments, and then you have to do like just like half 50% on the remaining one. So it's kind of like all the problems. Of course, like if you're doing 80% on each assignment, then that's more than enough, right? But I'm just saying like that's kind of set up so that if you kind of work more at the beginning of the course, then you can forget more about the end of the final assignments, which is good because that's when like everyone is full of things to do, right? So I'll still like let you know towards the end of the course, kind of like, oh, by the way, you have completed this percentage. You just need to do this remaining stuff on MyLab, but it's kind of more like designed so that if you work a lot more at the beginning, then like you have to worry less about the end. And still like the way I set it up, the settings for each assignment do allow you to do late submissions without penalty, because I'm not grading them. So like it's more important for me for anyone just to work on the problems. They will still have like, so they will have like a deadline, but it's kind of like a fake deadline. It's just kind of like to kind of guide you like, oh, by if you're working like if you're not late running late on the course, like that's kind of by when I would expect you to finish the stuff. But if again, like if there's like a week where someone has a lot more stuff to do, then yeah, you can just like finish that assignment later and there won't be any penalty. And like so that's kind of the idea. And then these 2 other things are very small. So once like once I give you like a particular assignment on these topics, like I'll let you know. But it's it's like from time to time, like maybe I'll put like some true false questions or something like that, and I'll give you a few days to think about it. And then you just upload your solutions on Canvas. So this will be like more sporadic. It's not something you have to worry like on a very regular basis. So once we get there, like I'll let you know. I don't think I may give you one of like a conceptual assignment for you to work on next week, but probably I won't make it due next week. I'll give you like a few more days. So is that okay? Are there any questions so far? So good. Yeah.
So is the homework graded on accuracy?
So the MyLab definitely, because like you do have unlimited attempts. So, but yeah, like to get the point on a particular MyLab problem, that would be great on accuracy. And then these two will be also great on accuracy. Like the GeoGebra one is kind of like different because I mean I'll be showing you GeoGebra like throughout the semester. This is more like kind of like taking pictures of certain animations, like I'll show you. So it's kind of hard to not get it like work at the on the first attempt, because it's just like it's more like a visual assignment. So it's just more for you to know how it works, like that you can actually use things to visualize like the stuff we work on. And then the only thing like that is not going to be kind of graded on accuracy per se is kind of like the workshops, but you'll get like feedback, on what you did wrong. It's just that your grade won't depend on that. But everything else, yeah, it's kind of graded on accuracy. But it's not too hard to get those points just based on how like I set it up. Because again, like for MyLab, you have, for example, limited attempts and things of that sort. Yeah, is that okay? That's your question. Anyone else? And yeah, like for the exams, that's kind of the breakdown of the exams. Again, I'll give you some practice exams and more information once we get a little bit closer to the specific dates. Probably like I'll start sharing like all the exams and things like that, like 2 weeks before the exam takes place. So that's when you have plenty of time. Basically, also, so the course is based on 500 points. So the idea, like, the way we'll do like the letter grades is that basically this is like a preliminary letter grade cutoff. So for example, if you get to 385, you're guaranteed a B. Depending on the particulars of the exams, if the exams scores are low or whatever, then that can be adjusted. So maybe the B starts at 370 by the end of the semester. I don't know, like, that will be decided later on. But, if you get 385, then you're guaranteed a B. That's kind of like, so it's not like, your score will be at least as good as the ones that are determined by these rubrics, but they could, be better. I mean, the letter grades can start at a smaller amount if there's like a necessary an adjustment is needed. But like for example, like I do like to set up the classwork. By classwork, I mean anything that's non-exam related in such a way that it is very feasible to get all the points on the classwork, because like you just can get more attempts. So like the way I like to think about it is like, say you get like 150 or 145 points on the classwork, then that means that to get an A, what you need like 300 points on the exams, and the exams are worth 350. So like 3/350, that's kind of like 85, 86% or something like that. So I'm just saying like like if you do the classwork is literally class work. So if you do the work, it won't be too hard to get all those points. So like, based on that, you can kind of like estimate how much you would need on the exams. But again, like that can be modified depending on just how they end up working out, like in terms of the scores. I can let you know, like for example, the first exam, like the second exam in terms of scores is better than the first one. Like the first one is not necessarily too bad, but students do tend to do better on the second one. The final, the only issue that it has is that it's a lot of material. So it's like So yeah, like the scores, like it's kind of like what I guess slightly of a roller coaster. The local match happens to be around the second exam, and then there's like a small drop for the final. But yeah, like it's like it is possible to kind of like based on this, like if you did really well in the first few midterms, like you can go like into the final more relaxed because at least oh, I'm like I only need like 30 points on the final to pass the course or something like that, something silly like that. So um but as I said, I wouldn't worry too much about this, but as after each exam, I'll kind of give you like an update on how everyone has been doing, etc., etc. So again, like it should be easier for you to reassess how that's working. Is that okay? Questions about this? Okay, so that's more or less what I wanted to mention for now. As I said, like just because I have never recorded the online version of sorry, the honors version of multivariable, I think I'll just record this class, which is why I'm doing using the computer for. I do like I'll send you the link. I do have like recorded classes for like the regular 251, so I'll share those links as well. So if you want, you can like see a little bit ahead of time the topics that I'll cover. If you go to modules, I mean, there's a bunch of material that I have posted here. Like I'll let you know later what you need, but yeah, there's like a course from fall 21, which is like the one that I tend to refer to because that one was all online. So it was easy to have generate notes for it because like yeah, we just like you would have like the Zoom meeting and then you would just post whatever you wrote on your iPad. So usually what I'll follow during class is like the notes from that semester. And so at the end of each class, when I send you like an announcement, I'll let you know, oh, we roughly covered these pages from this PDF. Again, like because it's like the honors version, like I may go up sometimes depending a bit more on a tangent, depending on what you ask me, but like again, like 95% of this course is indistinguishable from like the regular one. So it's still like a pretty good like guide for what you're supposed to cover. So if again, like if you for some reason want to review material before a class, or you cannot just come to one class or whatever like works best for you, you can just like watch the video or like read the PDF or whatever you prefer. So again, at the end of each class, I'll kind of like let you know what we did corresponds to roughly which pages on those PDFs. And then for again, the other stuff that I got posted here, you don't have to worry too much about it for now. Like I have a bunch of like optional videos that like I think they're kind of fun. So again, like sometimes like I mean, like one of the quiz problems can be like, oh, watch this video. Like one of the possible quiz problems would just be like watching this video and I'll ask you something about it or things like of that sort. So, um, but yeah, so now my plan was just to move to discussing like, just give you like a quick introduction to what we're going to do like multivariable calculus. So I don't know if there are any other questions before we switch topics a little bit. Okay, cool. So yeah, in the meantime, like again, like if anything comes up, you always feel free to email me. And if you came late, as I was mentioning, like I'll always try to be here like 30 minutes before class anyways. So, and I'll stay also after class. So let me explain this. The first thing that I will do, which is talk about vectors, and I'll tell you why vectors show up. So as I was saying, like this course is really like just let's take Calc 1 and redo it, basically. So what's the first thing that you see in Calc 1? Well, Well, after you spend some amount of time talking about limits, the first important thing that you talk about in Calc 1 after limits is like the derivative of a function, right? So if you have like a function of one variable, then you see the graph. The graph is a curve, right? So the graph is a curve. Okay, and you know, you have the tangent line. If the function is kind of nice enough, at each point on the graph, you would have like a tangent line, right? And the derivative is the slope of the tangent line, as hopefully you remember. So, you know, the equation of a line in general is y equals mx plus b, right? But this m, which is the slope, would be the, you know, like the way that this ends up working out is just like the derivative of the function with respect to x. Let's say this is the point x. Okay, so you know, basically in Calc 1, that like the tangent line and you know the slope is kind of like how much the line is tilted, right? So like kind of because the slope is a tangent of the angle, right? So the direction of the line in Calc 1 is already determined by the derivative, right? So in Calc 1, the derivative gives you the direction of the line, the direction of the line. But kind of what I want to emphasize here is that the derivative, in a sense, is just like a single number, right? So, but the derivative is just a number, so. Okay, so what do I mean by that? First of all, that just like a terminology thing, like numbers, from time to time, I'll refer to them as scalars in this course. So what I'm trying to say, let me just kind of give you, let's begin with some vocabulary. So if I say something like you know, a scalar, by that I just mean a number. So actually, it's a little bit more complicated than that, but it's like a good approximation to like a first way to think about the problem. So what are things that you would refer to as scalars kind of like in the real world? Like temperature. So like, you know, if you say like the temperature is 50 degrees Fahrenheit, like that's just a number, well, next to the units, right? But it's just like 50 degrees. So you don't have, the point is like when you specify the temperature, you don't have to say like it's 50 degrees to the north, right? Or 50 degrees east. That doesn't make a lot of sense, like, you know. So some things that are scalars. So here are some examples of scalars. Oops. So the first one is kind of like temperature. This one is a useful one to have in mind for the course, actually. Another one is actually the mass. So again, like you would say, like the mass is 50 pounds, but when you say 50 pounds, like you don't have to give like a direction to specify the mass, right? So it's just like a number, again, a number followed by a unit, but it's like in front of the unit, you just have like a single number. So the mass. Also, the electric charge kind of works the same way. I don't know if anyone knows another example. What could follow this? Yeah. Speed is a good one. Yeah, and that's like and it will be a nice distinction later on that we'll make. Speed is a good example. What's another good example of a scalar? What else? Another one. Just think about something that you don't have to specify the direction. Sorry? Age is, okay, so I'll use time, right? So like for like as a proxy for age, because yes, like if you say 10 seconds, you don't say 10 seconds north or 10 seconds south. Like that would kind of sound a little bit weird. So another one that's nice is energy, if you have seen that, like so. Okay, so what that I'm trying to say is that, you know, there are many things that you just like need a single number to specify them, and the derivative in cup one just happens to be one of those things. So, you know, like if you have, just to give you another example, right, like a more concrete one, if y equals x squared, then, you know that the derivative is just 2x, right? Y prime is 2x. And so that says like once you know the value for x, right? Like the value of the derivative is just twice that number, the x value. So again, like that just happens to be a number. Okay, but so the first thing you can do which is you know, kind of like in this spirit of generalizing calc one, the first thing that you notice is like, okay, so the goal in a few lectures, like we won't start with that right away, but so the goal would be something like, instead of like having a function that depends on a single variable like x, then you can be like, so this is more like of what we want to do. So this is now top three. So instead of like having a function of just x, like I'll think of y as an independent variable as well. So I have something like a function of f of x comma y. So since I'm already using the variable y, I have to introduce an extra variable, so I'll call that z. So you have something like z equals f of x y. What's an example of these? Something like z equals x squared plus y squared. Okay. That's kind of like the closest, like the easiest analog of the parabola. You know, just square the second variable as well and add them together. What ends up happening here is that the graph, okay, so the graph is no longer going to be a curve. If you, and again, we'll talk about this a bit later, but so the graph is no longer a curve. Okay, so what is the graph? Actually, the graph ends up being like, that's why I asked for the umbrella. Okay, so then, let me open this here. So the graph ends up looking like a surface. Okay, so the graph becomes a surface, like for a function of two variables, the graph is a surface. So let me just oh, and that's more or less how the graph for z equals x squared plus y squared looks like. It will look kind of like a, you know, like a cereal bowl. Like it's called like a paraboloid, but it really looks like this. We'll like actually we'll talk about this one a lot later on. Okay, so that's how the graph looks like. Okay, so then you ask like the same question. So for a function of one variable, kind of what you were interested in is like the tangent line, right, to that function. So now, oh, actually I have some tangent lines. Okay, this is like a tangent line. So for a graph that is like a surface, like the tangent, like the idea of a tangent line is not good enough. Like actually what you want is something called the tangent plane. So basically you want something like this. You want to put like a piece of paper, like, you know, all over the, you know, different places of the surface, you put like a notepad, like a sticky note. So like a bunch of like tangent planes here. So let me try to draw like mini pieces of paper. So yeah, let me put something on here. So instead of like, So instead of like a tangent line, then we will use a tangent plane. We will try to find the tangent plane. Oh, sorry, yeah.
Does the tangent plane still intersect the surface at one point?
Okay, so even it will touch the surface for sure, but even for already for functions of one variable, the tangent line can touch the graph at several points, right? So when like the easiest one is kind of like something periodic like sine or cosine. If you remember something like sine of cosine, right? Like the tangent lines at bunch of points will intersect. So it's not it's not so much whether it touches it once or more than once, it's that near the graph, if you start zooming in, like the graph becomes more and more indistinguishable from the approximation, like which is the point of the tangent line, right? So the tangent line, the idea is to approximate the graph once you look close enough here. After you move a little bit away from the given point, then differences can really become a lot more noticeable. But so the idea is kind of like the same in this context. The point of the tangent plane is that really, if you were to, zoom in, like near a particular point on the graph, then like the graph really becomes very close to the tangent plane, in a way that can be made more precise, and that's where all this Taylor stuff approximation kicks in. But again, like that's not something too much. I may bring that up later once we talk about that, but for now, it's kind of like just think, oh, it looks close enough, but yeah, it could or could not like touch the surface at more than one point. Depends on the specifics of the the graph. Definitely, it would at least touch it at one point because that's where it's passing through. But beyond that, there's really not like a big requirement on whether it happens multiple times or not. So instead of a tangent line, we'll find the tangent plane. Is that okay so far so good? And then, okay, so where is like this stuff about vectors that I'm going to tell you about? So the thing is, there are different ways to think about the problem, but so okay, let me put it. I will try to give you like the more geometric answer. So let me. So the question is like, what's the analog of like the equation of a plane? Like, the equation of a line was something like y equals mx plus b. You want to know what's the analog of that for a plane. So I won't give you like the answer right away or today, but at least I'll tell you something that's kind of useful to keep in mind. So if I wanted to find the equation of the plane, so again, think of this as the analog of y equals mx plus b. So say we're after something like that. Okay, I'll tell you later, like once we talk about planes more properly, I'll tell you how that looks like. But if I just have like a plane in space, I don't know if anyone's taking linear algebra, but that's something you'll talk about a lot. So planes and lines and things of that sort. But if you have a plane in space, turns out that a very useful way to think about the plane, or like a useful way to specify a plane, is just by specifying what I'm going to call a vector, but let's just call it like an arrow for now. A good way to think about how to specify a plane space is by specifying an arrow that's perpendicular to the plane. So think of the plane as a piece of paper or like this tablet, like literally. And so I'm going to give you an arrow perpendicular to it. So for example, if you have like the desk, which is a plane, if you extend it indefinitely, the arrow would just be pointing like towards like, the ceiling. So it would look something like this. Like if you want, I can even make it like taller. Like the idea is like it would be like a 90-degree angles to the desk. But if if your plane is kind of tilted, you should correspondingly tilt the arrow. Okay, so this, like trying to specify, like, to specify the arrow, I have to kind of like single out a direction in space. And so that's what vectors are going to be for us. So vectors are just going to be kind of like arrows in space. But you see, like they kind of come in very naturally in this problem because it will, later on, you'll see it will be like a convenient way to like specify a plane. So to specify a plane, what I'm trying to say is that you have to draw something like this, which will be called the normal vector. You have to specify something like a vector that's perpendicular to the plane. So here, this will be called the normal vector, which would be a vector. And again, I'm going to put vector in quotes because I really haven't told you what vector is so far, but vector, think about it as synonymous with arrow. Okay, so there, what I'm trying to tell you is that you don't need like the difference now is that you don't need like knowing a number does not suffice in this problem, right? For the line, you can say y equals mx plus b. So you give me m, right? You give me a number for the direction. But here, it is not enough to say like a number. Like if you say like the number is 3, I don't really know what that means. I have to kind of tell you I'm pointing this way in space. So that's the difference between the problem before and the problem now. Yeah.
So you could also, for the same one, you have one put it like this or put it down like this.
Right,
Does
right.
that matter at all?
It won't matter. There will be there will be a few ambiguities, but yeah, like it could point point like towards like the ceiling or the floor. That's more or less okay because that will be parallel. I'll tell you about that later as well. And also like, if you have a vector that's perpendicular, you can double it and still it's perpendicular. So what I care about more about is more or less like the actual direction, not how much it ends up being. And it's also like direction can be multiplied by, can be like, 180 degrees, the different orientation, and that would also be fine. So up to those few things, like it's more or less unique basically. But yeah, the point is, the more important point for now is kind of like that you do need like some sort of direction. It's not, if you just give me a number, that doesn't cut it in this situation. Is that making sense? So, but yeah, like there will be like a couple of like ambiguity that will appear, but they're not as hard as you could be worried about. Okay, so this is the important thing that I'm trying to emphasize here is that direction matters in certain problems, and this is kind of like the first one where you can see that make an important difference. So let me tell you now like a little bit more about vectors because that's where really the course begins. So first, maybe I think I don't need this umbrella for anything else. So you give it to me, right? So let me tell you about vectors. I see, I guess it is. Okay, we still have like 30 minutes. So let's talk about vectors for a few minutes. So yeah, like a way you can think about vectors for us is like some sort of arrow in space. So that's how I want you to think about them. So let's call them like arrows in space. So something like this, something like this, something like this. So all of these 3 arrows would be considered like vectors. Okay, so what does it mean? For to say that there are arrows in space, it means 2 things. Like first, it matters where they're pointing. So they could come with like a direction. So they have like information about direction. They have a direction. And they also have a size, okay? So like, this particular arrow has a given size and I could double it and that would have a different size, twice as big, right? But so they also have a size. They have a size, which is like also called length. It's a bit there's a bunch of like different names for this. Like it's also sometimes called magnitude. It's also called norm, but again, most of the times I'll try to use at least 2 or 3 of the names at the same time so that it kind of sticks like the idea that they're just like different. There's a bunch of like different terminology for the same thing. So in terms of like notation, like, to differentiate, like, like usually with like in math, like if you wanted to write like a number, you would write something like A, B, or C, or X, Y, Z, like something to represent a number. For a vector, you could use like a single letter, but then when it comes to the writing, it would be hard to differentiate that from like, from just like a number. So like the conventional is when you like, are like writing it, like an arrow on top of the symbol. So something like, so this would be like the vector V, this one V would be like a vector U, and this one would be like the vector W, for example. So every time I'll write something with an arrow on top of it, I'll always refer to it as a vector. If you were typing this on the computer or whatever, then like it's not convenient to put like arrows, so you write that in bold letters. So so in terms of notation, so we use either like an arrow, use an arrow like above the letter. Or type it in bold, or write it in bold. But again, like, it usually we'll just say like something like the vector or something. So we'll kind of like emphasize that it is a vector. But I'm just saying like, when you are reading like the textbook, it's not so common to see it with the arrows on top of them. So you'll just like differentiate them because they come with bold letters. Okay. So again, like vectors, like they're not just like numbers, like they also point in certain directions. So like I can give you some examples of like vectors, which you may be already familiarized with, like more like day-to-day examples. So here are some examples of vectors. Now, like the most basic example of a vector would be something like the velocity. Okay, so like a velocity is going to be a vector, which is different from the speed. So that's like this like a subtle distinction, but it's something like the velocity. Because for example, if you say, well, you were driving 50 miles per hour, like to actually make that into a vector, you have to say 50 miles per hour north or south or east or west or whatever, whatever you want. So like you have to give me like some sort of like direction. So you see there, like the direction could be like north, east, south, west, whatever, and the size would be the 50 miles per hour. Like, it also comes with like some number associated to it. So something like velocity would be a vector. And for that one, you typically just use the letter V for velocity. Like then acceleration would also be a vector. Then if you have taken like a physics class, then like a force would be like a vector as well. And then what else is like a vector? Like similar to this one, like like something like an angular velocity would be a vector. That's a little bit different, but yeah, like than this one, but it kind of has like a similar has a similar spirit in terms of definition. Like angular momentum would like momentum, it's like a vector. What's called like the linear momentum. Or like just momentum. It's also like a vector. You know, something like an electric or magnetic field. Like an electric field is also. Magnetic field. I'm just putting you like a bunch of examples so that, you know, just to emphasize that depending on like the context, then yeah, you'll kind of like use different letters, you know, to like emphasize, like, you know, like once like you're thinking about them like as representing certain physical quantities, they tend to come with their own special letters, right? In the math classes, like typically we just call like them V, U, and W. That's more than enough for us. But you know, like they will adjust themselves, like depending on the context and how you want to use them. They will like, you know, come with their own like you know, own preferred like notation or symbol for it. Okay, but so there are a bunch of like things that are vectors, but again, the important thing about them is you know, to specify them, you do need like the direction. That's kind of like how they're different from just like an ordinary number. Okay, so okay, so like the first thing that you could say is that you know, when you have numbers, you can add them together. So you can say 3 plus 5 equals 8, right? So you can add numbers. There is a way to add vectors, so it's kind of useful to think about that first. So let me tell you how to add vectors. That's the first thing to know about them. Okay. So the definition will become more clear in a moment once I kind of like explain it in a different way. It may look a bit odd now, but the idea is like, let's say I give you two vectors, like let's say V and U. So I'll give you V and U. Let me put them like this, just to make my life easier. Okay, so I have these two vectors, V and U, and I want to add them. So I want to kind of come up with something that would represent V plus U. So my like what I'm trying, what I will explain to you is what is this thing. Okay. So the idea is that you know, if you have this vector here, you have this vector here, they're kind of like in different places in space. That's okay, but we kind of want to kind of them to, in a sense, interact with one another. For them to interact with one another, you have to bring them together. Okay, so like imagine you just take one of these two vectors and you move it around. So I should have said this. I can take a vector and I'm not allowed to move them around as long as I don't change their size nor direction. So for example, you know, if I just move with this vector, it's still pointing upwards, right? And I still haven't changed its size. So in a sense, like this is kind of considered the same vector. Or like this one would be considered the same vector if I just move it like this. So vectors are allowed to be moved around as long as you don't change their size nor direction. So if you have a vector here and you have another vector here, you can move them around so that one begins where the other ends. So let me do that. Like, it's kind of like a copy paste. So you're allowed to copy paste vectors all the time. Oops. So, so yeah, let's copy paste this one. I'll make a clone here. And I also can copy paste this one. I'm trying to make them so that they look like identical, like in terms of size and direction to the ones I drew before. Okay. So that, maybe I should could tilt this one a little bit more so that it's a bit better, so let me tilt it. Yes. So, well, roughly that's how they look. Okay, and so you have these two vectors, and the idea is like, you should think of these two vectors as two sides of a triangle. And so the addition will just correspond to the third side of the triangle. So just complete the triangle. So that the addition is like the third side. Is that okay? Is that making sense? Yeah.
Do we know the direction of the vector?
Okay, yes, that's a good question. So it will, okay. So this one, let's say, will start, you know, it will start, you start where B ends. So this one will start. And this is like the fun part that I'm about to show you. Let's call this vector 1 and this vector 2. So this one will start where 1 starts and ends where 2 ends, okay? Where 1 and ends where 2 ends. But there's actually something a little bit suspicious about what I just said, which I don't know if it's super obvious, because one question you could ask like is how do I know which one is 1 and which one is 2, right? And that so let's think about that for a second. Okay. So let me say. Okay. So imagine that I had taken you, right? So again, I'm allowed to copy paste them. I'll just copy paste it here to have some space to work with. So I'm going to think now this as the first vector, okay? And I'm going to copy paste B, put it here. I'm going to think now about this one as the second vector. Okay. And if you were to follow this recipe, like, you still have two sides of a triangle, right? You complete the triangle. Okay. And now this one starts where 1 starts and ends where 2 ends, right? But I mean, like, if you do everything perfectly to scale, it takes some time to convince yourself. But I mean, really, this side should really be a copy paste version of this one. So this one, like, which you could call like U plus B if you like, because now U was the one that I called 1, and this is like one that I called 2. It really does match with V plus U, meaning that it doesn't matter which one you call 1 and which one you call 2. So really, like what I'm trying to say is that my point of doing it in these two different ways is kind of to persuade you that V plus U is V plus U. There will be a more algebraic way to do this, where it becomes more clear, but it's kind of like nice to do it with some pictures at the beginning to kind of convince yourself that that's kind of plausible looking. Okay, so what I'm trying to say is that, when you have two vectors, you bring them together, form the triangle, but it doesn't really matter which one you call 1 and which one you call 2. You can build the triangle in the two different ways, and they, the third side will be the same. Is that making sense? Like, so, like this definition, like, looks like can be added at first, like, if you have, haven't seen it before, but it really kind of it is set up so that it matches, for example, how you would add forces. So for example, you have like an object, you apply different forces to that object. So the net force would match to the sum of vector, like the vectors representing those forces. So it's kind of all kind of built so that, you know, those operations like do agree physically, do agree with what happens physically. So what I'm trying to say is that you have like, you know, you could have like, this is like probably something you have seen maybe. I mean, it's like somewhat extreme case, like you have like a mass M, and then you apply like, you know, so like now I would call them force, so like I'll call this F1, like for force one, you know, and then like you would have maybe this other one, you know, imagine like, you know, there are like maybe force applied because like you put some ropes to the object, so you're like, it's kind of like a tension. So then you have like another force here. Okay, and then you know, the net force, like if you make like the clone, like if you make the copy, like the, if you copy paste this, the net force acting on this object will correspond, actually it does match up to how the vectors add up. So this would be like F1 plus F2. So this would be called like the net force. The nice thing about looking at it from this perspective actually is, you know, is that if you copy paste the green one here, let me maybe do the picture separately. On this end. So you have F, and you have B and U, make clones of them. So let's put you here. And be here. And so the yellow vector that I have been drawing that corresponds to the sum corresponds to the diagonal of this parallelogram. Okay, so this is why this addition law is sometimes called the parallelogram law. And it also kind of explains maybe a little bit better why it doesn't matter the order, because it really is the same diagonal of the same parallelogram. So that's another way to think about doing this. So let me write it in words. So like this is called the parallelogram law. Which is just that if you use, if you build a parallelogram out of U and V, if you U and V, then the sum corresponds to one of the diagonals of this parallelogram. Okay. Then we can send some questions. So that's geometrically what the you know, like the addition of vectors ends up being. Okay, so now like just to start moving in like more algebraic direction, let me explain this in a slightly different way, which is more, which is really how we will work with these things. So in practice, it's not that I'm expecting you to draw the arrows, you know, to find the sum. It's just like a nice way to think about it, but you know, for all these problems, we'll use more algebra to actually determine the answers. So how can we compute this sum using some algebra? So So here's like a more algebraic way to do this. So in order to do this like more algebraically, what you need to do is like use coordinates. So you have to use coordinates. So what do I mean by that? So for example, you draw the x-axis, the y-axis. So once you have like an XY axis, right? You know, since I was saying like the vectors are allowed to be moved around, you can just move the vectors so that they start at the origin of the coordinate system. So the idea, once you have like an XY axis, the convention is to draw the vectors so that they start at the origin. So you draw the vectors. So for example, in this case, like V, like looks like V would land somewhere in the first quadrant, right? Looks reasonable. So let me draw it here. If you copy paste V, it's somewhere in here. And if you again copy paste it, I probably use somewhere in here, right? So it probably landed in the fourth quadrant. Again, maybe let me try to make it a little bit bigger. Maybe here's where you is. Okay. So far so good. The thing is like once you have that convention, then like the vector will just happen to end somewhere, right? It terminates at a given point. So from that perspective, you can think of the vector as being used to kind of like specify a point on the plane. So once you do that, the vector like can be used. Once you do this, the vector gives you the position of a point on the plane, right? So just to like make this more clear, so for example, let's say this vector, I don't know, maybe this point could be, I don't want to make it isosceles or anything, maybe this point could be 3, 4. So maybe the green vector ends up terminated at the point 3, 4, okay? And then maybe you would be, okay, I'll put it a little bit smaller. So let's say that this point where you terminate is going to be, maybe, okay, looks a bit, let me make it a little bit smaller than 3. So like I'll put it like 2.8. And then it's like the y coordinate should be negative. Maybe it would be like, I'll put 2 just to make the numbers nicer. So I'll put 2 here, and then I'll put the y coordinate to be -1, just to give some specifics. Okay, so what I want to say something is like if I write something like this, or when I write something like this, what do I mean? I mean the vector that starts at the origin and finishes or terminates at the point 3, 4. Okay, so this is like the vector that starts at the origin, starts at 0, 0. So right, the origin is here. So here's the origin, right? That goes from 0, 0 to 3, 4. And if I write something like u equals 2, -1, by that, I'm almost done, I promise. So by that I mean the vector that goes from 0, 0 to -1. So from this perspective, like, once you have like the XY axis, the vectors can be used to keep track of like points on the plane. Is that making sense?
Does it matter if the like curving the-
Oh, right. So like, that's actually what I was going to say. Like, the book has like this, not weird notation, but the book has like to distinguish it a little bit from just the actual point, they will use like more like pointy brackets. Like in practice, it never causes any confusion. Like, and also when you're writing, like, whether you write it like like, curvy or pointy, like it's hard to differentiate. So I won't kind of go into the distinction, but like, because like the important thing is like I'm writing that there's like a vector in here. So by just saying that this is a vector, I mean like literally from from the origin to that point. So there's really no confusion ever that occurs like for that. So I'm not saying that the vector is this point. I'm just saying once you force them to start at the origin, there's really, they are like a perfect tool to keep track of those particular points. So if you do that, then the nice thing, what happens, if you do this, I mean, it takes some convincing, but I should have it like. I mean, again, like you have to redraw the parallelogram and the triangle or whatever. It actually, what ends up happening is that the point where this lands or ends is really what you get by just adding the corresponding coordinates. That's kind of like the nice thing of the addition. So these will really just be like the point 3 plus 2 is 5, and 4 minus 1 is, or 4 plus minus 1 is 3. So what I'm trying to say is that b plus u, it really just becomes 3 comma 4 plus 2 comma -1. So you do the addition in the most like naive way you could think about it. You just add the first entries and then you add the second entries together. So like that's kind of what so let me like let me put it even like more like emphasize this even more, like just show you all the steps. So you get like 5 comma 3. So what I'm saying is that like another reason why the addition ends up being defined this way is that like once you have coordinates, it just matches what you would get if you like add the individual entries of of the vector. So let me write that in words, and that would be the last thing I'll tell you today. So to add vector, if to add vectors algebraically, you just add the like the corresponding entries. So like in general, like like another way to say this is like, if you thought of the vector v as being v1 comma v2, and the vector u as being being u1 comma u2, what I'm trying to say is that the sum v plus u is a kind of like a vertical addition. In this case, it would be v1 plus u1, v2 plus u2. Okay. That making sense? So so that's kind of why this ends up working nicely in terms of the algebra. But in order to have done this, like you do need to kind of like, first choose like a coordinate system, which is fine because like that's kind of like will be implicit in everything that we do. But it's kind of useful to know that there's like a more geometric definition for adding them in terms like of like this triangle business. But when it comes to computations, like this is how you would be expected to find what the addition gives you. So it's like very simple, like algebra stuff. What I'll do, what is a little bit more interesting, and that's what we'll start talking about next time, is that, you know, with numbers, you can add them, you can also multiply them, right? So you could think about, oh, maybe let's try to multiply vectors. So the thing that happens is that there are kind of two natural ways to try to do that. The most obvious thing doesn't work. The most obvious thing just being like, you know, maybe just multiply the corresponding entries. That actually is not like a useful definition. So like the two actually interesting ways to do it are called the dot product and the cross product. So that is what we'll start talking about next week. What the dot product becomes actually easier to define. And once we have done that on Monday, we will talk about the cross product. Okay, so, but yeah, let's just, I think we spent today at 5:10, right? So let's end here, and next time I'll explain how.